Hello all, this is our presentation on image restoration by matrix completion using Schatten capped pnom. Before we dive into the details of the procedure and algorithms, let's first have an overview of what is matrix completion. Matrix completion is the process of recovering a matrix with only partially observed entries. In figure 1, it can be seen that the white squares which denote missing entries are estimated through the matrix completion algorithm. This is done by taking into account the structure of the observed entries denoted by the green squares. Let's move on to see some applications of matrix completion. In our work, we are majorly focused on image restoration, which is the process of restoring a higher quality image given the low quality input. Since images are simply nothing but intensities of different pixels, it can be easily modeled as a matrix. In figure 2, it can be seen how an image which is damaged due to various factors has been restored to a higher quality version as shown. Figure 3 on the right denotes a common problem of image degradation due to transmission, corruption, etc., which can be reversed using image restoration techniques to an image as shown in the slide. Other than image restoration, matrix completion is widely seen in various other areas such as collaborative filtering for recommendation systems, motion capture, face recognition, etc. Now, let's move on to the matrix completion formulation. Let D belonging to R m cross n denote the matrix corresponding to the input image with partially observed entries. Without prior knowledge of the underlying problem, the matrix completion task is highly ill-posed. Fortunately, since most information and energy of a matrix are concentrated on its dominant singular values, it is natural to assume that the underlying matrix is of low rankness. The low rank conclusion can also be seen from the high correlation that exists between the pixel intensities. Thus, we'd want to restore a matrix X which is of the same dimension as D such that its rank is reasonably minimal. Equation 1 denotes the same with an added constraint that the entries of X should be matching with those of D over the observed index set omega of D. The observation operator P omega denotes the same as shown in the slide. Equivalently, the same constraint can also be posed as X omega is equal to D omega as shown here. But due to the highly non-convex and discontinuous nature of the rank function, the rank minimization formulation for matrix completion has been proven to be NP-hard. To tackle this issue, there are several convex and non-convex relaxations which have been introduced as surrogates to the rank function. These help in studying the rank minimization problem approximately. Broadly speaking, the existing methods for matrix completion can be categorized into spectral regularization based methods and matrix factorization based methods. In spectral regularization based methods, the singular values or their variations are utilized to recover the missing entries in the matrix. In matrix factorization based methods, the original matrix is approximated by the product of two or more small size matrices. Compared with the spectral regularization based methods, this type of method is usually computationally cheap and less memory consuming. However, the rank of the matrix should be known in advance. Now, let's see the mathematical formulations of some well-known surrogates to the rank. The first one is the nuclear norm minimization. The nuclear norm of a matrix is simply nothing but the sum of the singular values of it. The optimization problem is posed similar as before. The nuclear norm is the tightest lower convex bound of the rank function. However, the nuclear norm minimization is considered suboptimal since all the singular values shrink simultaneously in the solving process and thus often leads to the overshrinkage of the rank. On the second column, we have the truncated nuclear norm regularization, a non-convex surrogate which does not punish the largest R singular values. Hence, these largest R singular values are preserved. Here, R is just a parameter. On the third column, we have the Schatten P norm, which is closely related to our work, is yet another non-convex surrogate which is defined as shown. It has been proven that the matrix completion result based on the Schatten P norm is superior to that of the methods based on the nuclear norm when P lies between 0 and 1. It is also clear that the Schatten P norm generalizes to the nuclear norm when P is equal to 1. The last column is the low rank matrix factorization, which comes under matrix factorization based methods. When the rank of the matrix, say R, is known a priori, then the constraint that the rank of the restored matrix X should be less than or equal to R can be easily posed by writing X as a product of two matrices whose rank at max can be R. This step converts the optimization formulation from constrained to unconstrained. It should also be noted that it is still a non-convex optimization problem. Seeing some of the common methods in literature, I would like to draw your attention to the challenges that are yet to be tackled. The first challenge is that the underlying matrix is usually approximately low rank instead of exactly of least rank in practical applications. Thus, the matrix with the least rank may not be the optimal solution we aim for. A suitable optimization model that can balance between the rank and the nuclear norm of the underlying matrix should be redesigned to replace the rank minimization formulation. The other challenge is that the larger singular values and the smaller singular values of a matrix usually represent significant information we want to preserve and the error or noise we want to remove, respectively. Thus, an appropriate measurement function that can promote the preservation of larger singular values and punish the smaller singular values to zero should be redesigned to improve the recovery accuracy of the matrix completion operation. Thus, The newly proposed non-convex surrogate function, called the Schatten capped p-norm, focuses on the smaller singular values in the matrix and thus balances between the rank and the nuclear norm of the matrix. The Schatten capped p-norm generalizes several existing norms. By adjusting its parameters, the Schatten capped p-norm can degenerate to the Schatten p-norm, the nuclear norm, and the capped norm, etc. The Schatten capped p-norm is formulated as shown by equation number 2. Here, sigma I is the ith largest singular value of x. Tau, which is strictly positive, denotes the predefined threshold used to filter the singular values, and p is another parameter which lies between 0 and 1. Therefore, the Schatten capped p-norm can be utilized in the matrix completion problem to preserve significant information corresponding to the large singular values and filter out the insignificant noise corresponding to the smaller singular values by adjusting the values of tau and p. For optimization and convenience purposes, equation 2 is rewrote as shown by equation number 3. Moving on to the matrix completion procedure, the optimization problem is same as we have seen before and is represented by equation number 4. Equation number 5 represents the unconstrained formulation of equation number 4 by taking into account the Frobenius norm of the difference between x omega and d omega. The Frobenius norm is defined as the square root of the sum of the absolute squares of its elements. The value gamma in equation number 5 is a regularization parameter. I would like to remind you once again that x omega has entries only at the observed index set omega of t, remaining entries being 0, and d omega has the value 0 at indices which are not observed in the input matrix T. Equation 6 converts equation 5 once again to a constrained optimization problem by introducing E omega and W as shown in the slide. The brief procedure for optimization after this is to obtain the augmented Lagrangian function for equation 6 with y and z as the Lagrange multipliers and mu as the regularization parameter. Then, following the framework of alternating direction method of multipliers, which breaks down the problem into smaller pieces, the original problem is optimized through various subproblems iteratively as shown by the following equations. Equation 7 gives the optimal solution x by fixing E omega and W. Here, omega c is the complement of the index set. Similarly, equation 8 solves for E omega by fixing x and W as shown in the slide. Finally, while fixing x and E omega, equation 6 gets simplified into the following minimization problem with g and lambda defined as shown. I would like to once again draw your attention here to take note of the fact that the pth power of the Schatten capped p-norm of W, which is non-convex in nature, cannot be solved for an analytical solution W. Thus, an iterative procedure is adopted to solve the same. Let's now see how to solve for W. Theorem 1 gives the approach. It says that the optimal solution W for the last subproblem is given by Q sigma R transpose, where Q and R are the left and right singular vector matrices of G, respectively, and sigma is a diagonal matrix with the ith diagonal element sigma I star, which is solved by the minimization problem posed by equation 11. Here, delta I is the ith singular value of the matrix G. Thus, the final solution for W is constructed as shown in equation 12, where R denotes the rank of the matrix G. But we have to keep in mind that we have not yet given a solution for sigma I star. Let's see how to solve for it next. Here we have theorem 2, which lays down the procedure. It says that the minimal solution sigma I star for equation 11 is given by delta I when tau lies in the closed interval formed by 0 and tau star, and xi prime when tau is greater than tau star. The value of tau star is calculated as shown here. But to solve for xi prime, equation 14 is adopted. It is simply 0 when the ith singular value of g lies in the closed interval formed by 0 and v dash, and is given by xi star when the ith singular value of g is greater than v dash. The expressions to calculate v dash, which is a constant, is as shown in the slide. The value of xi star is solved by classical gradient descent approach by initializing the value at the first iteration to delta I. I would like to point out that the values tau star and v dash are simply nothing but thresholds to tau and delta I, and thus control the solution to the minimization problem on the last slide. This is the final pseudocode for the algorithm with the update equations for y omega and z given by lines 5 and 6 respectively. Rho here is used to update mu. To start with, initial values of y omega, z, w are all set to d omega, and these are used to get the values of x at the first iteration. The loop continues till maximum iteration, or when the relative error between the two consecutive values of x is less than some tolerance level. Finally, we also show you our own results obtained by implementing the Schatten capped p-norm based matrix completion. The implementation was done in Python language using the popular library NumPy. Figure 4 on the left is a random mask experiment where 75% of the pixel entries of the original image are made 0. The middle image represents the restored image, and it can be clearly seen that it closely represents the quality of the original image. Figure 5 on the right side masks the original image with Chinese text over it. Thus, wherever the text exists, the pixel values are 0. And once again, the restored image is in close correspondence to the original image. For implementation details and result, please visit the given link. Thank you for listening.